The password for today's attendance is Subhanallah. Okay. The password for today's attendance is Subhanallah. Okay, finish? So inshallah we'll have your quiz on Thursday. How many classes we have left? Do you know?
Around 9, 10?
Ada 10 lagi?
9 kot.
9 lagi?
8 madam.
Tiba-tiba kurang, setiap kali tanya lagi kurang.
Ni betul madam, 8. Should be 8.
Kita ada berapa minggu lagi? Kita minggu berapa ni?
Minggu ke 10.
Kita minggu ke 10. Kita ada 4 minggu. So 8. So kita minggu 10. Kata tolak lah minggu last tu kita bagi awak study. So kita ada 3 minggu. 3 kali 2, 6. 6. Kita ada 2 kelas tu MOSFET maybe. So 4 kelas untuk BJT. Okay. We're doing okay, I guess. So kita minggu last tu tak ada kelas. So if you have any question, you can call for class. We can have a discussion in the class if you want to ask anything. So saya bagi, so you need to study from now. If you need any consultation for the semiconductor, it will be in the final week. If you want to ask anything. Okay. So kita ada lagi 3 minggu kelas. So kita ada minggu ni, minggu depan tak ada kelas kan? Cuti kan? Cuti lah?
It depend kat madam.
Bukan cuti midterm ke? Apa it depend madam? bukan midterm ke break?
No, it start on Wednesday.
Oh.
We still have 1 class if you want, madam.
If you want or if you need it. That's the different thing.
If you ask me if I want, I don't want. Boleh tak? Tapi need maybe. Okay. Need maybe. Then will reduce me talking. So, sekejap. Okay. So, kita ada ni. Tak payahlah kelas minggu depan. Okay. So, semua nak balik kampung. Siapa balik kampung? Ke semua dah kat kampung? You are all at home, right? Nobody in URA?
Oh, Faiz.
Shut up.
Except for Faiz. Okay lah, the rest of you are at home. So awak bahagia akan beraya dengan family. Baguslah, bagus. Okay, saya tak boleh balik kampung. So this tahun kedua tak balik kampung. Rasa ramai orang. Kesian lah. Kesian orang tak boleh balik kampung. Kesian, satu kesian orang tak boleh balik. Kesian mak ayah kat kampung pun kesian. Sebab dia orang expect nak jumpa anak-anak masa raya ni lah. Tiba-tiba anak-anak semua tak boleh balik. Oh, okay. Let's start today's class by watching a video. Okay, and this is a recent video in BBC News. Okay, it's about semiconductor. Kadang saya suka tengok news-news apa-apa yang related to kelas saya, engineering ethics ataupun semiconductor. So let's watch this. Berita keluar. Share sound. Then my video. Okay. Can you see?
Yes.
Oh. Yep.
I don't know. So
So we're about to go into the wafer fabrication plant, and it's a biosecure environment that even dead skin cells
can you
can
see?
disrupt.
Can you? Dia
The
smooth
process
tak?
of getting dressed to go in is really quite elaborate.
This is enough.
Aman.
Boleh.
Boleh lah.
Kalau tak smooth, saya bagi link.
Over the course of 3 months, what starts out as
Okay.
silicon will travel around on this track. It will be repeatedly stenciled, then cleaned with chemicals, and stenciled again until, in the end, it comes out looking like this. This is a pack of 25 wafers. They'll be diced up and sent to companies around the world, where they'll go into everything, from our computers to our cars to our mobile phones. It's basically been a perfect storm. When the pandemic hit, car factories closed and automakers stopped ordering chips. But COVID also forced people to stay at home, causing an increase in demand for chip-heavy goods like laptops, gaming consoles, and 5G phones. So tech companies swooped in to buy up that stock. Then, when the car industry recovered faster than expected, automakers raced to buy the remaining supplies of chips, and the world was left short.
If you ask me today, I already see the booking into this year, which we have never seen that before, right?
You're fully booked this year.
We are fully booked.
Okay. Ini saya nak tutup ni. Here's another interesting Cisco boss. Semiconductor shortage a big problem ni. 1 minit. Jom kita. Can you hear me?
Yes.
Yes.
Let's watch another video. Tak kuat saya cakap. Saya tak tengok lagi video ni. Tapi dia keluar apa-apa lepas habis tu. So let's see. So the title is Cisco boss. Semiconductor shortage is a big problem. Okay, let's listen.
Right now, it is a big problem, as everyone has read, I'm sure, and it's it's because semiconductors go in virtually everything. And what happened is when COVID hit, I think everyone thought that the demand side was going to decline significantly, and in fact, we saw the opposite. We saw the demand side increase. So what happened is all of the manufacturers like us and car manufacturers and everyone sent lower demand signals to the providers of semiconductors. They then reduced their capacity, and at the same time, demand went up instead, which was a complete shock to so many of us. And now we think it may be exacerbated because customers, we're afraid, are placing multiple orders or there's so much demand in the system because they're trying to get ahead of it, that the overall demand right now could actually be exacerbated, but that's okay. We think we got another 6 months to get through the short term. The providers are building out more capacity, and that'll just get better and better over the next 12 to 18 months, we think.
Okay.
In other words, in 3 years.
Tapi still there are...
At this point, I am.
Okay, stop sharing. So COVID also affecting semiconductor. So kita ingat dia affecting life. So affecting everything, including semiconductor company. In a way, they say interesting. It's a shock because they think the demand will be less sebab semua tak berjalan, especially on the car industry. Because you know, even oil pun kan gas Petrol pun going down mula-mula tu is shocked everybody sebab semua tak ada keluar. So therefore orang tak beli kereta, therefore orang buat kereta tak order cheap. So sebab nak buat kereta-kereta ni, it will be like, I think more than 60% of a car now is electronics. It's no longer mechanical. Kalau macam sekarang ni kita otomotif dalam mechanical kan, kita punya kat engineering kan, otomotif kat mechanical. Nanti otomotif tu saya rasa kena ada, kena revamp betul, memang 50% be electrical. So kita akan jadi, our department lah will be very strong sebab semua nak have to be electrical. So kereta-kereta using chips and chips semiconductor chips yang dia orang pakai ni dalam kereta, they involves high temperature. Sebab kan, have you seen an engine before? Masa dia tengah running panas kan, you cannot touch it, right? It's very hot. So therefore they're looking for alternative for semiconductor materials yang boleh withstand high temperature. So apa contoh-contoh semiconductor material yang boleh withstand high temperature? Apa karakteristik yang perlu ada? Faiz, you keep quiet first.
Sorry.
Eventually I will ask you lah, kalau tak ada jawab juga. Ya. Okay, yang lain? Cuba tu. What do you think is characteristics of a semiconductor material that need to be able to withstand high temperature, for example in automotive punya application?
Direct band gap.
Why direct band gap? Why? Itu the masalah yang kau jawab, you kena ada jawapan why lah. Kalau tak, then how do you justify the answer? Why, Azam?
Because in indirect band gap it will release additional heat.
No, why direct band gap release addition? Oh,
Indirect.
So indirect will give additional heat. Sebenarnya heat produced by the photon tu tak banyak sangat pun. Recombination, that really, heat tu taklah banyak sangat compared to the high temperature heat of the car. Siapa nak jawab lagi? Soalan-soalan macam ni mungkin keluar final exam.
High lattice.
Apa? High lattice?
Lattice strength.
Lattice strength? What do you mean? What do you mean? Do you mean atom with a more atomic weight or atomic number? Oh, ni kita pergi masuk nuclear physics. Kita tanya Faiz lah. So what are the characteristics which are important for high temperature?
This one that I read here talking about wide band gap devices.
So you're not supposed to read, you're supposed to think. You're supposed to think. So yes, why? So give me an example of wide band gap. Why wide band gap material? Give me an example of wide band gap material, Faiz, and why the answer is wide band gap.
Silicon carbide is one of them.
Okay, so why? Why is we need large band gap? Kadang-kadang panggil wide band gap, large band gap.
Because we want to be able to control the operation of the semiconductor, right? So if wider the band gap, the less temperature dependent.
Why is it less temperature dependent?
Because the electron needs more heat and energy from outside to be excited to conduction band.
So silicon is 1.1 eV. What the band gap? What is silicon carbide band gap, Faiz?
Good question. I don't know.
You don't know? You're supposed to memorize this. Silicon carbide ni dia punya apa nama ni?
3.26. There you go.
dia punya bread and butter. Dia buat eksperimen on silicon carbide. 3.2.
3.2.
So 3.2, ada 3.6. It has a range depending on the different types of polytypes of silicon carbide. So 1.13 times. So silicon carbide has 3 times larger in terms of band gap compared to silicon. Therefore, you'll be less affected with temperature. So when you are dealing with high temperature and radiation environment macam nuclear ke space angkasa lepas tu, you want a high wide band gap material such as silicon carbide, gallium nitride. Itu antara yang common wide band gap material. Okay. Tapi dia akan lagi mahal compared to silicon. Kenapa?
Sebab silicon senang dijumpai.
Satu, silicon senang dijumpai. Kedua ialah the processing of the material is not matured yet. Maknanya nak buat kuih lapis kan. Silicon tu semua orang dah tahu dah kuih lapis nak pakai resepi apa, temperature apa semua. Tapi kalau silicon carbide ni it's something new. And people are still doing research. Kita orang pun tengah buat research on kan Faiz, silicon carbide punya effect of radiation to silicon carbide. So benda tu baru. So people still are not many companies in the world that can manufacture silicon carbide semiconductor devices. Tak banyak. Sebabnya sekarang ni Intel semua tu on silicon. So kalau dia nak pergi silicon carbide, dia kena invest a lot of money, another type of like equipment to make it. So COVID.
Also researching on germanium, if I'm not mistaken.
Germanium is, what's the band gap for germanium?
Well, for Intel, if you talking about Intel, germanium band gap, let's see here. Germanium would be 0.67.
See,
So low.
Yeah, smaller than silicon. So no point lah sebut germanium tu kalau kecuali untuk application yang
basically they try to make smaller chips. That's their target because they try to get down to 0.7 nanometer, if I'm not mistaken. 7 nanometer, 0.7.
Why germanium will help that?
Something about that's based on the quantum side. It's like smaller atom size, so like smaller package.
So it may be smaller but it's more expensive. Satu, germanium. Satu lagi dia tak tahan. So it depends on the application. Semiconductor ni is very much devices depending on application. So when in the quiz or in the exam, read the question carefully. What is the application? What is the environment that I was talking? So maybe saya akan berkata pakai kat kutub utara, North Pole. Right, so maybe the question is North Pole. So you need to think, okay, North Pole, what's the environment like, and what is the suggestion that you should suggest. Okay, saya akan kata compare seorang pakai kat desert, seorang pakai ke North Pole. How the performance of the device will be. So awak kena berfikirlah. Alright. So COVID is so now the good news is because there's a a lot of demand for the semiconductor. Now dikatakan super hot lane. So sekarang ni dia tengah cuba nak perbanyakkan lagi the pengeluaran semiconductor. It means that for this kind of industry, maybe they will expand and need more workers. Mungkin nak lagi ramai pekerja. Mungkin. Right, sebab dia memang dia terdesak, sebab dia nak kena ramai orang dalam tu. So mungkin dia akan increase the number of hiring. Itulah. So maybe you want to target some companies. Okay.
Madam.
Yes.
Malaysia is the factory in Malaysia mostly manufacture or design?
Mostly manufacture, basically banyaknya assembly. Dia fabrication and assembly. Design very rare, ada sikit dekat Intel design, tapi most of the design coming from US. They come and fabricate in Malaysia and then they assemble in Malaysia, then they packaged in Malaysia. So kita heavy on dia panggil back end. Kalau dia ada dua tempat yang banyak company semiconductor ni, satu di utara di Kulim, Penang, Intel Penang, Kulim, Infineon. Dan satu lagi tempat yang banyak ialah Melaka. Ni 2 tempat. So biasanya macam itulah, kalau orang Melaka, you cubalah apply. Most higher chances you will get. Dia orang suka ambil orang lokal. Katalah awak orang Penang, awak guna alamat Penang apply. Mungkin lagi senang sikit dapat kot, sebab you know why? Bila saya pergi Infineon, saya pernah visit sekali student kita EIT dekat Infineon Melaka. So dia kata oh, saya tajalah sambang-sambang engineer tu. So dia kata what is the current trend you see with the student now? Dia kata one of the problem that they see is very difficult to retain the staff. Maksud dia kata that your generation ni suka melompat kerja. So dia kata tak sama macam zaman-zaman dia dulu semua. So you know the company need to invest a lot to train you. So imagine kita orang train awak, tiba-tiba train awak setahun, awak dah terror betul, awak lompat. And we are supposed to like gain. So sekarang ni kita kena train orang baru balik yang tak pandai dan tak cerdik tu. So in the end they are frustrated because of this. So that's why dalam interview dia akan banyak tanya, dia akan check budak tu akan stay ke tak. Macam dia akan tengok psyche budak ni. Kalau budak ni rasa nampak gaya macam dia kata oh I will go wherever the best option ke apa, memang tak dapat lah kerja tu. Dia kata sekarang ni memang dia nak orang yang yang loyal. Sekarang ni biasa budak-budak zaman sekarang ni kurang loyal, dia katalah, sebab gaji besar sikit macam. So jadi susah untuk dia orang to run the company. And then dia akan bagi banyak insentif. Kalau orang tu stay, dia akan bagi banyak insentif nak suruh orang stay daripada orang jump. Tapi still itulah. Tapi kalau awak jump, awak cepat naik pangkat lah. Sebab tu budak-budak akan jump. Bukan budak pun, saya dulu jump. Saya ingat masa mula saya kerja dulu, saya kerja setahun dekat semicon company. Saya kerja 10 bulan kat Unit 10. Lepas tu saya masuk UIA. Masa tu pun mak saya duduk bising. Kan mak kita zaman-zaman dulu kerja satu tempat tu sampai mati. Macam sampai pencen. Dia orang tak tukar tempat kerja. Ayah saya Mardi, daripada start degree dia sampai dia PhD habis apa semua, dia kat Mardi tu lah. So jadi bila saya ingat mak saya kata, Fas, apa ni, dia marah saya sebab tukar kerja. So dia kata, orang duduk dah tempat-tempat, duduk senyap dah, okey dah gaji apa semua gitu kan. Kita dah fikir it's a better opportunity somewhere else. So saya ingat mak saya kata tu, saya tak kisah, tapi lepas saya masuk UIA saya stay lah, because I already found where saya suka, tempat yang saya suka, dan tempat yang saya boleh spend the rest of my life macam tu. Tapi kalau adik saya yang dapat private, so kalau kat private memang akan jump sebab tak secure. Private tak secure. Kalau government you secure. So saya daripada private engineering company pergi masuk Unit 10 pun private. So saya tak bersuka sangat dengan Unit 10 punya environment tu. Saya masuk UIA, saya suka, plus dia macam stable lah. So saya duduk lah. Tapi adik saya, dia IT manager, tak berhenti tukar, lompat. Tapi gaji dia berlipat-lipat kali ganda lah asyik tukar. Tapi dia private, tapi there's no security. Dia akan boleh dibuang bila-bila masa. Tapi gaji besar. Macam tu lah, kalau awak duduk kat private, awak kena be able to, macam duduk kat Petronas for example, ramai awak kena retrench kan. Ramai kena tu, tapi gaji dia orang besar sebelum kena retrench tu lah. Tapi there's a high risk that you'll be lay off. Tapi kalau government ni gaji taklah besar mana. Okey lah, kau jadi profesor boleh lah besar sikit. Kalau tak jadi profesor, setakat lecturer cabuk tu, tak besar gaji. So tapi dia punya tu is security. So apa-apa jadi government takkan buang kita. Paling-paling pun dia akan cut gaji kita half ke. Tu pun lepas private akan buang semua orang dah. Tapi tak pernah jadi lagi lah dekat UIA, at least gaji kena cut ke. COVID macam mana pun government, itulah government satu hal, pergi pinjam duit kat luar. Sekarang government, government staff got 500 ringgit duit raya daripada government. Awak tahu kan? Can you imagine dengan negara tak ada duit punya lah teruk, dia boleh bagi 500 ringgit seorang. Imagine kalau kita ni berjuta-juta pekerja. Alamak, this is recorded. No, jauh ingatkan. Okay, thank you. Sebab orang kena study lah. Alright. Kau tak ada apa nak remind. Okay, good. So sebenarnya I was telling Faiz, kalau kalau awak berfikiran jauh sikit kan, semua benda yang saya suruh buat laser, apa nama ni, photo detector ke LED, semuanya ada presented on my, semua kelas-kelas sebelum saya ni record. Kalau pergi dengar yang tu, awak dengar saya punya komen, you will get 100% in the presentation. Tapi I think none of you go. Ada tak orang pergi tengok? Saya rasa tak ada, sebab tu awak kena komen kau-kau dengan saya tu. I mean, kalau awak cerdik sedikit lah kan, you will go watch that. Sebab ada satu kelas tu yang master class, so dia present bagus lah, master class lah semua. So and then you can see how they present, apa benda dia letak. So kalau buat semua tu, you will get 100%. Tapi tu saya saja tak cerita nak tengok siapakah yang kita tengok tak ada. Okay, so early effect. Have you come across? No, I'm sure you come across early effect, early effect before, or early, or we call it early voltage. Do you still remember what's early voltage?
Not sure.
Macam tak ada harapan, saya rasa tak ada harapan untuk awak ingat. Not sure tu saya rasa memang tak ada. Dia not sure tu sebenarnya jawapan dia no. Betul tak?
I just remember the graph.
Which graph?
This
This graph? You remember this graph?
Yes.
So in your first year, you just memorize what is early effect. Okay, so why is it important? Why is it important for you in your first year? Because of this equation. Because in your first year, you have to do calculation, right? You have to calculate the collector current in terms of the of the voltages. So this is the equation that you use, and in the equation there's this term, the early effect, early voltage. So normally in your first year, the lecturer will give you the value of the early voltage. You just plug it in. So you just maybe have seen this graph whereby what is early voltage, it means that if you do a characterization of your, for example, your IV, this is current versus VCE of your BJT. If you do for various biasing of the base to emitter voltage, you will see that dia ada slant. Ideal, if you remember ideal macam mana, ideal patut straight je. The ideal, there's no slanting. So but actually in real life, when you do measurement in the lab, you will see it becomes like slanting like this. And this Pakcik Early ni, this Mr. Early, found out that if you pull this to extrapolated it to the x-axis, it will come to one point. And this point is called the early voltage, and this voltage you put in the equation here to come up with the current, to be able to calculate the current accurately. Okay, now in our class now, we want to learn why do we have early voltage, why is it slanting. Dulu tak kisah, awak just kata dia slanting, maka kita terimalah dia macam tu. In our class, in the fourth year, you're supposed to understand why is the current here is not constant. In idea that you learn before, dia constant lah. As you keep on increasing VCE, doesn't increase the IC. Awak masih ingat ke? Saya rasa kita dah lama tinggal BJT ni, awak masih ingat ke? Macam mana ni? Do you still remember apa nama tu? Kenapa dia tak nak? Dia tak nak ni. Sekejap. You hang dah. Interesting. Saya punya MacBook ni something wrong lah. Biasa MacBook tak pernah hang. Kenapa ni? Ensure. Okay. Screen share stop access shared window is closed. Okay. So we just give some kita refresh sikit atau kau semua masih dalam mode optoelectronics. So this is BJT, bipolar junction transistor. Kat mana to show how it works? So if you remember, we talk about this. We talk about the current inside BJT, right? Kita dah cerita kan? Ke belum? I can't remember. Apa benda kita dah go through BJT ni? Have we gone through that it will diffuse through and then be drifted? Dah ke? Dah kan? The energy band diagram of BJT dah kan?
I don't remember.
Buka kau punya note. I don't trust your remembrance or your I trust your book. So buka buku awak mana tak pernah cerita lah. Kat mana kita berhenti sampai kat mana BJT?
Tak pernah cerita.
Tak pernah cerita apa-apa?
The last one is this diagram. That you can.
Same.
Okay, so dah tak boleh masuk secondary effect lagi. So kita kena cerita apa benda BJT tu lah. Okay. Maka kita akan cerita BJT tu apa. Ke saya tak boleh cerita awak cari sendiri. Yang mana awak nak cari sendiri lah.
Masuk beli effect lagi.
Apa Faiz?
Dan kalau cari sendiri, kiranya secondary effect tu boleh study ke? Boleh teach dalam kelas ni?
Boleh apa?
Dan kalau suruh cari apa pasal the how BJT works dulu. Lepas tu yang kita nak belajar dalam kelas ni boleh?
Boleh apa, tak faham. I don't understand what you're trying to say.
Yeah, do we need the knowledge prior to learning what's in this class?
Yes, you need it. You need to speak English then I will understand. Yeah, I don't understand. So, okay. You know, my whole learning, I did my A-level sampai PhD dekat UK. So sebenarnya I'm very bad in, not very good in talking in Malay, especially in front of public. So sebenarnya tak bagus. Saya rasa macam tak bagus. Saya rasa macam ada kekurangan. Nak masuk TV pun saya akan bercakap campur dengan English. Kan orang Melayu kan suka orang cakap Melayu je kan. Saya tak pandai lah. So awak try lah belajar dua-dua English dengan Malay. Okay, so now let's look. Okay. So let's draw. Now kita draw the BJT. So BJT is very similar in terms of how it works as compared to PN junction. Okay, so kita akan draw ni. Okay, so let's draw this NPN. NPN. Can you see there are two diodes over here? Yeah, where's the diode?
E and PN.
So you have here, over here, and then like this, right? Betul? Okay. So what are the terminals for BJT?
Emitter, collector, gate. Habis.
Okay, so you have the emitter terminal, you have the base terminal, and you have the collector terminal. The tiga terminal of a BJT. Okay, now, so there are a few if you want to operate the BJT in terms of as an amplifier, how should you bias the transistor? This is first year punya knowledge. If you want to use the BJT as an amplifier, how should you bias the transistor? Najwa? Senyap Najwa. Ada ke Najwa? Ke tak ada suara Najwa? Are you there Najwa? Macam mana kita patut bias ni?
Hidup.
Kenapa? Tak dengar Najwa. Are you saying something?
She's typing.
Oh, he's typing. She's typing. Aiman, macam mana kita nak bias ni? Sementara Najwa typing lah. I'm waiting for your benda yang awak type.
Saya masuk Anjana tu cakap Allah.
Okay. Saya tak tahu angina ni apa. Sakit kot. So, moga awak cepat sembuh. Aiman.
Forward.
Huh?
Forward.
Forward kat mana? Forward kat mana?
Base.
So you are saying we should like okay. So put positive at the base.
Yes.
Yang lain?
Negatif.
Kat mana? Kat mana?
C.
Dekat mana?
C. Collector.
Negatif kat collector. Lagi?
Emitter. Positif.
Positif. Okay. But awak agree ke Solehin? Dengan Aiman ni, kawan awak.
Yes.
You agree?
I agree with forward bias.
You agree dengan semua benda ke apa?
I agree with forward bias, but not really sure about the rest.
Kenalah bagi jawapan.
I think so.
Okay, I think you should revise your first year electronics brothers and sisters. Okay, if you
ke collector and base, kemudian negatif dekat emitter.
what
So it's like a bit inverted from what Aiman said.
So in order to answer this, you need to know the different mode of operation of a BJT. I think in the slides, dia ada apa nama cut off mode. Cut off mode is where the diode is off. Then you have the saturation mode and you have the forward active mode. Saturation mode and the forward active mode. Active. If you still remember in your first year, most of the calculation is in the forward active. Why? Because you want to use it as an amplifier. You have a gain. When you have gain, it means it's in the forward. When you have gain, it means that you are operating as an amplifier, and to work as an amplifier is in the forward active mode. Saturation mode, you use the BJT. You still remember is for benda yang constant. For example, logic. Use saturation. Okay, now if you still remember, nanti awak buka balik buku elektronik ataupun you go and read a bit. Forward active mode means this. Kadang kita panggil dia FAM. The forward active mode means you forward bias the base to emitter junction. So this junction you forward bias, and then this junction collector current you reverse bias. Okay, so you reverse bias the junction. If you do this, it will enter the forward active mode basically, and you have gain. Okay, so kalau if it's forward, kalau saya forward lah, saya buat ni forward. Kalau forward, this will enter saturation mode. So saturation mode, you forward bias the base to emitter junction, and you still forward bias the base to collector junction. But in our class, we will learning mostly on when we use it as amplifier, which is the forward active mode. Okay, now, so negative. Okay, so this diode now is in the forward active mode, which is we bias it correctly. So kalau tu now, so macam kalau sini awak kena draw, kalau zaman-zaman dulu kan, awak draw dia jadi gini, dan yang ni negatif. That's how you bias the transistor. Okay, now, so now we understand how we bias it ni first year lagi. Okay, next, now we want to learn how do you get current inside BJT? Anybody can tell me? So how can you get the current inside a BJT now that we bias it this way, based on your understanding of the PN junction? Hambali, can you tell us? Because it's just PN junction, right? So tell me, electron pergi mana, hole pergi mana, what happens?
Yeah.
That's how you get current, right? By movement of electron holes. You still remember the name is bipolar because both electron hole gives current inside BJT. So which means that you need to talk about electron hole both. Boleh jawab tak Aiman? Hambali.
No.
Kenapa tak pula? Ni PN junction je pun, right?
Tahu memori yang pendek je.
Macam mana? Kau nak kena ambil kuis dah hari Khamis ni. So it's supposed to you should to know. Azam, can you tell us? Azam?
How the current produced?
Yes.
It will move from E to C.
What will move?
The electron
Move in terms of what? Is it, when you talk about current, there are only two major mechanism of current.
diffuse.
So, what will diffuse?
The electron will diffuse.
Okay. From where to where? Oh, so kalau dalam exam, kau kena jawab penuh tahu. So I will not ask you banyak kali macam ni. You just supposed to tell me in one sentence how the carriers move. So, the electron will diffuse from
from the right region, the left region to the right region.
to here direct.
to the P first and then to the N.
So it will diffuse in the P and then diffuse to the N. So it will diffuse to the P and then again diffuse to the N. Is that what you're saying?
Yes.
So still diffusion from this, in this region, still diffusion.
A drift. So,
Okay. So repeat again your statement.
from N in the left, the electron will diffuse to the P, and from P, it will drift to the N.
Okay. So what happens when this electron, so the electron here in the N here, is it majority or minority?
Majority.
Majority carriers will diffuse to the P, right? And then hole over here. So because we talk about electron hole, so hole over here will also diffuse to the N at the same time. So when a lot of electrons, so what about the depletion region here? Is there any depletion region here?
Which one? The left junction.
Ya, kita panggil base to emitter junction ni. Is there any depletion region?
Very small because it is forward bias.
Yes, because it's forward bias. So you have like depletion region, but it's small. Okay, how about this region over here? The base to collector junction. Is there any depletion region?
Why?
Yes, and it is bigger, right? So this bigger, so maybe we draw like this. Okay, so basically let me repeat. So this majority this electron will diffuse through the P side to the base region. So the electron from emitter side will diffuse to the base region. Okay, now when the electron arrives here, when the electron arrives from emitter to the base, what happens here in the base? So you see electron in P region. So what will happen, you think?
You will drift it to the collector because the
No, not yet. Not yet. Here, what happens? Electron here in the P region. P is what is the majority carrier in P?
recombine.
Hole. So you have a lot of hole in this region, and then suddenly you have a lot of electron coming here. What happens to the carriers? Free electron meets free holes. You have recombination. So recombination means you lose carriers or you gain carriers.
Loose carriers.
Okay, so for example, if 4 goes here, 1 will recombine, right? 1 will recombine, and then so the rest of it will diffuse. So some of the electron will recombine, and majority of it will be drifted. So they reverse bias kan. So they be drifted and being collected at the collector. Now, when you have recombination over here, what happens is the number of free holes, in this region becomes less. So what happens is this circuit will replenish the hole. So you will have hole current will provide the hole. So there will be IB. And this base current is the current that when you are the base region at the base region, when you lose the number of holes, the number of holes will be replaced by the outside current. So this is the base current. So base current is big or small as compared to the emitter current?
Small.
Small, because the recombination is small, right? So it depends on number of recombination. So if the transit time, if the electrons here are staying in the base region not too long before it's drifted, then the probability for recombination is less. Therefore, the base current will be less, and the direction is like this because it's the direction of the hole. So you're going to replace the hole over here. So, and then the direction of the electron emitter current is the opposite direction of the flow of the electron. So it will be like this. Okay. So most of the electron will be collected at the collector and become IC, and where this collector current coming from, most of it is from IE. That's why the equation that you learn in your equation in your first year, IE equals to IC plus IB, right? Because of all of the major carriers coming from the emitter. So, and then you will lose some as the base current, and the rest will be collected at the collector. So dulu awak hafal, now you know why the current is like this. Okay. Apa nak cerita? Okay, this explanation is in terms of the structural explanation. Remember for PN junction, saya explain juga kan structural macam ni. But in the quiz or the exam, I want you to explain in terms of the energy band diagram. So PN junction saya dah explain juga recombination apa semua kan macam gini. Tapi dan saya explain in the video about how it works in terms of energy band diagram. Now, without opening the book or YouTube or internet, I want you to draw the energy band diagram of this BJT at zero bias. Zero bias dulu. Dah draw ke itu? Tak ingat. Have you drawn? Sebelum tak?
Not yet.
Okay, so I give you 2 minutes. 3 minutes. Draw me the energy band diagram of a PN junction. Of a BJT, sorry. At zero bias. Kalau ada apa-apa soalan tengah-tengah saya ajar, you can always ask. Tak payah tunggu saya habis, tanya je.
NPN kan, madam?
Ya, ni NPN, yes.
Unrelated question. Dr. Salmian tak jawab apa lagi, madam?
Oh, tak, sebab benda tu dah delay. So, band tu dah lambat.
Okay.
So, saya kata awak free lepas pukul 1 ya. Oh, dah angkat dah.
Alright then.
Okey lah, ada 2-3 orang dekat situ.
Tak nak buat apa.
Dah siap draw, let me know.
Madam,
Huh?
how will IB produce the base current?
Apa?
Is it the IB
The base current is produced due to the recombination of the holes.
due to recombination?
So nanti
Bagus.
Aina, you can show your drawing. Kalau tak siap pun draw je apa-apa yang dah siap. You can take a photo and put it in Telegram, or you can just put it in the camera. We can see it.
Okay, done also. I think. Oh wait.
Saya ambil gambar.
Okay.
Can I show it?
Okay.
Oop, no, not the one. Scanning. There we go.
N P N. Okay.
Yeah.
Finish, Aina.
Select the column from cursor to small. Describe combination.
Kau lambat ambil gambar. Dah kan? Awak boleh letak dekat kamera tu je. Cepat sikit. Dah.
Dia tak detect.
Oh,
Kamera tak detect.
sebab
Dia
ada.
detect face je.
Sebab dia ada background tu. Dia tak boleh nak detect. Okay. So semua orang tengok yang dalam Aina bagi tu. Do you agree with this, Solihin?
Fermi level.
I'm not asking you.
The familiar is
Apa, Solihin?
No, because the familiar level is only on the right hand side. There should be familiar level and meet up and the right hand side.
Tu je ke? Is there anything else?
And yes, that's all. Maybe the depletion region is quite big.
Okay. Alright. I will show you how to draw it. Senang gila. Okay. So I'll tell you how to draw it. Apa? Apa Faiz?
No energy gap.
No energy gap?
Not me, that was Azam.
Apa? Tak dengar. Apa?
Energy gap.
Energy gap?
Energy band gap.
Tak ada energy band gap?
Not label naik arrow to the top. EG.
Oh, tak ada labeling. Dalam exam, make sure label everything. Conduction band, valence band. Kalau ada energy band gap, berapa EV. Kalau saya cerita dalam soalan tu ada cerita IV. Kalau tak ada, awak dah cari. Sebab it's open book, right? You put there, give you marks. So, every details counts. Okay, so now. Saya nak buat apa tadi? Okay, so the drawing is like this. So, sebab dia zero bias paling senang di dunia apa-apa pun. What you should do, the first thing you do is you draw the Fermi level. Continuous. So, Fermi level should be continuous. Lepas you draw the Fermi level, baru you draw, is it P or N? So, you know for the, apa nama ni, NPN. Apa benda ni? So, the NPN. So, N should be, the Fermi level should be close to the conduction band. So, draw dia macam ni. And then, also in this here, I didn't say what type of semiconductor material. So, you assume. Kalau exam pun, you need to write what you assume. You assume is this a homo junction. So semua junction tu same material. So maknanya the band gap here should be the same height. And then this is the N. Then you draw the P. The P, it should be the same. Saya ada ruler ke kat sini? Macam mana ada ruler je? Ada ruler.
Saya madam punya kena apa tap and hold kat satu tempat. Dekat pen
Tapi tu untuk straight. Tapi saya nak ruler, nak tengok dia nak jadi ruler.
Oh, okay. I see what you mean.
Scraper. Macam tak ada je. Tak ada. Ni tak, dia tak high end. Low end. Okay, so ni saya kena guna tangan saya sendiri. So saya, and the height should be oh, kalau saya nak lagi best saya copy je lah kan. Mana ni? So saya just copy dia. Just nak copy. Macam nak copy lah. Okay, bersabarlah. Maka tak jumpa cara nak copy. Oh. Ni copy. Copy, paste. Oh. Okay. Ni. Oh, sabar. Saya main-main dengan benda ni. Copy, paste. Okay, so sebab kenapa saya copy paste, so that the Fermi, the band gap is the same. Okay, done. So then saya delete lah Fermi level ni. Okay, so saya ada N. Now saya ada P. And then saya nak N balik. So saya copy je lah sekali lagi.
Kita paste je.
Boleh
paste
paste
je.
Saya paste je.
Jadi dah copy.
Betul. Saya paste je marker kat sini lah lebih kurang. Okay. So lepas draw 3 ni, awak sambung je lah dotted line. Cuma yang ni tak perlulah banyak kali ni. See? As simple as that. So make sure the band dia punya band gap tu ni samalah kalau is homo junction, unless saya beritahu dia material lain. So this is zero bias. Okay, so then you know this is conduction band, this is valence band, and so on. Now I want you to draw. So this is so kita label ni emitter, ni base, ni collector. Now I want you to draw, this is at zero bias. I want you to draw it for forward active mode. Now, without looking in the book or YouTube, draw me the energy band diagram in a forward active mode. Macam ni. Forward bias the base to emitter junction, reverse bias the base to collector junction. Okay, give you 3 minutes to do it.
Okay, madam.
Apa Aina?
I was lost just now.
Awak terkeluar. So now I ask everybody to draw the energy band diagram for forward active mode. Okay, you forward bias the base to emitter junction, you reverse bias the base to collector junction. Anybody finish?
Hold on, just labeling. I think so. Let's try this. You serious, madam?
Huh? Okay.
Saya tunjuk.
You agree with Faiz punya tu?
Sama dengan Faiz.
Sama. P and so everybody's finished drawing. So tengok and show. Okay. Okay. So hopefully you get something similar with this. So you have the electron diffusing to the base and being drifted to the collector and being collected. So another thing, important thing which I didn't mention before, when you draw just now, we assume the doping concentration of the N and the N and the P the same, right? Tapi actually in real life, as a designer, we design the P type to be less doping as compared to the N. Can anybody tell me why? The doping at the P, the base region, is made lower as compared to the doping in the N of the emitter. Anybody can tell me why?
So that the recombination less happen at
Yes.
P.
Good. So why do you want to have less recombination?
So the more electron can drift to C.
So more electron will be drifted and collected because what is do you know the equation for gain?
IC equals to beta IB.
Beta equals to IC over IB. Like the gain equals to IC over IB. If IB is small, it means the gain will be higher, right? So therefore we want to design so that the IB be small, therefore the gain is higher. The amplifier will be a better amplifier. Allah. So therefore kita we dope it the emitter region less. So kadang kalau dalam exam saya tak beritahu, sepatutnya awak buat macam ni. You can see here. Can you see the doping in the base is less than the N? How do I know?
Fermi level.
Fermi level.
The Fermi level is further away from the conduction band. Ini lagi dekat.
Balance.
Okay. Alright. So the most important the doping of the base lah biasanya.
So emitter has the highest doping compared to others.
Yes, the emitter has the highest doping compared to others. Okay. So now we know how it works. So you should be able to draw the PNP. Mungkin dalam exam quiz saya suruh draw PNP. Yang tadi NPN kan. PNP ni sama je lah, kita balik. PNP just means that majority carriers now are the holes. So the hole will diffuse from the emitter to the base and then drifted to the collector. So dia dekat bawah ni, and the way they drift, dia pergi naik atas kan. Holes are like bubbles, it will go up. Okay. And okay, but you still have minority carriers, you know, moving. Okay, so then okay, dah kita faham tu, apa lagi yang nak tahu ni? Okay, this is the equation of the current gain beta IC over IB. Therefore we want IB to be smallest as possible. So if you still remember the equation for your emitter current in your BJT, it's actually the current equation of a diode. So this is the equation of a diode. IE equals to exponential VBE over VT minus 1. This is the equation of a diode. Because the emitter current basically is just a diode. It's just a forward bias of the base to emitter junction. So that's why the equation is exactly the same as the equation of a diode. Saya tak pernah tunjuk equation of diode. Ni equation of a diode. So, okay. Okay, in terms of the depletion region, you can see the depletion region is this is forward bias, it's small, this is bigger.
This amplifier, madam.
Apa?
Is it amplifier?
What is amplifier? I don't understand.
This work as amplifier.
Yes, a forward active mode work as an amplifier. It has a gain. Bila-bila sahaja ada gain, maka ia adalah amplifier. So forward active mode works as an amplifier.
For both NPN and PNP.
Apa, tak dengar?
For both NPN and PNP.
What do you think?
Yes.
Yes.
Yes lah, tak ada beza pun. It's just satu, the carriers, majority carriers are electron, the other one is hole. But if you want it faster, you want electron lah. Yang kalau you want to high speed, normally NPN is more favoured. Okay, PNP boleh juga. Alright. So, okay, kita dah belajar. Okay, this you learn in your first year. This current characteristics of a BJT. Kalau diode tahu kan, saya tunjuk ke diode macam saya tunjuk. Diode punya current equation, diode punya current characteristics saya dah tunjuk sebelum ni. Ke belum?
What the saturation, the reverse bias and then the breakdown current lah.
Forward. In the forward bias. So the simple, kalau diode characteristic of the IV is the current is IV. Sorry, this voltage. So this current is voltage for a diode. The current characteristic looks like this. I would still remember. Right? So this is the diode current characteristics. And this is linear. You plot it linear. Mana the axis of the graph of the y and x is linear. But if you plot it if you plot it log linear, ni saja ni cerita, ni tak masuk exam tapi penting orang research punya faiz. So if you plot it log linear, untuk orang buat FYP dan bidang saya ni penting lah. So kalau log linear, this will be, so this log, this is linear. Okay, how it would look like, it would look like this. So it will look like this will look like a straight line, and then from this straight line you can find we can calculate the ideality factor from the slope if you plot it log linear. So normally in research we don't plot it linear like this. We plot it log linear. And then in the reverse you will see you have a more increase here. You don't see, it's too small. Okay, so this is for diode. For a BJT, so this is the current characteristic for a diode. So for a BJT, it looks like this slide that I showed you. Ni, macam ni. Okay, so you have the collector current versus this is PNP. So that's why it's VEC, it's not VCE. So as you increase the VEC, okay, when we talk about diode dekat BJT, we talk about base emitter junction and base collector junction, right? So VBE and VBC, right? Voltage of the base to emitter and base to collector. But when we draw the current characteristics for BJT, we talk about in terms of VEC or VCE. So across emitter and collector. Basically, if you do the maths, it's just representing, it is similar as representing the VBC, the base to collector junction. So if you even increase the base to collector junction, it doesn't improve your collector current. Do you get me? So if the base to collector junction, kita ada junction dua PN junction tadi, yang sebelah base to collector junction, even if you increase the reverse bias, it shouldn't increase the current. Why? Why is stay constant? Anybody can tell me?
Best collector.
Why? Apa ni? 12.57. Kita end with this. Anybody?
Reverse.
Because if you look here, so we are talking about the IC. IC is collected here, right? And VEC or VCE, it basically is also representing the biasing over here. If you increase the bias over here, reverse bias, what happens to here? What happens here? If you increase the voltage?
Wider this depletion region.
In terms of energy band diagram?
Steeper.
It will be steeper. So let's say this is minus 10 volt. If minus 20 volt, it will be here. Okay. So jadi it's just steeper. So when it becomes steeper, does that increase the current? If this is steeper, does that increase the current? Yes or no? Solihin, does that increase the current? Solihin? Huh?
No.
Why not? Why not?
The region minority.
Why not?
Because at the region only minority carrier being diffused.
Mana pula minority kat mana? Why you talking about minority?
No, because reverse bias, if the depletion region is larger, then there's less carrier being moved the depletion region.
But we'll talk about this, the BJT, how it works. How do you get current? IC punya current kat sini banyak ke sikit? Solihin, the current that collected at the collector here, is it high or low?
Low.
Low. Hai. Aiman, the collector current collected here high or low?
High,
Why is it high?
because the electron from base drifting to collector.
Okay, so the electron, it's high because it's collecting the electrons which are drifted from the base to the collector. So the source of the current is actually the electron that been diffusing from the emitter to the collector. Okay, now you understand that. Now the question is, why if we increase the base to collector current, base to collector voltage over here, which is also the VCE, if you increase this, why is the current remains constant? It's not increasing, even if we increase the VBC in reverse bias. Anybody can answer, dan kita boleh tutup habis kelas kita lah.
Because it does not affect the emitter part.
So
the source of electron is from emitter.
So the answer is it doesn't change because the number of carriers that drifting are still the same. Right? If you make it steeper, it just makes the drifting, this electron will fall down faster. Tu je. It's a steeper hill, it means the electron will be collected faster. But it doesn't mean the current will increase. Right? So that's why, ideally, it becomes like this. This is an ideal diode characteristics whereby if you increase VEC or VCE or VBC, it remains constant. Okay, it's supposed to remain constant. It doesn't make sense. Why should suddenly it should increase? Okay, only at very low here because it's still collecting. At very low VCE or it's still collecting the carriers. Then after a while, that becomes constant. So, but it's a function of the base current. If the base current is bigger, if the base current is bigger here, it means that we bias the VBE bigger. When IB is bigger because we bias the base to emitter junction at a larger voltage. When you forward bias the base to emitter junction at a larger voltage, you have more current. Tu je what it means. Okay, so this is the ideal. In next class, we will be learning the non-ideal, which is the early. This is the ideal graph. The non-ideal is this. This is supposed to be constant, but now it's increasing. We want to, and this is what the scientist or experiment engineer found out. So we need to understand why, in the end, it's increasing instead of become constant. And we will learn that inshallah in the next class. Okay. So in next class we finish now how it works. You're supposed to be able to draw the energy band diagram and explain how a BJT works. So kita basic lah, tapi make sure yang dulu ingat. So if I change the temperature, I do something, I shine light to BJT. So you should be able to think what happens to the devices. Okay. I think that's all for today. Can we end the class next week? Kita ada berapa kelas? Kita ada 4. Saya rasa sempat kot kira. Sekejap kita ada kelas Khamis ni. Kita ada kelas. Okay, minggu depan tak ada kelas lah. Minggu depan kita bercuti raya. Saya pun nak raya dah, tak balik kampung pun. Okay, so can we have somebody to recite the doa? Aina, stay. I would like to talk to you. Siapa nak baca doa ni? Okay, Faiz.
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم الحمد لله رب العالمين والصلاة والسلام على أشرف الأنبياء والمرسلين وعلى آله وصحبه أجمعين اللهم اغفر لنا ذنوبنا ولوالدينا وارحمهما كما ربيانا صغيرا اللهم ارفع عنا الولاء والبلاء والوباء والفحشاء والمنكر المنكر والسيوف المختلفة والشدائد والمحن ما ظهر منها وما بطن من بلدنا هذا خاصة ومن بلدان المسلمين عامة إنك على كل شيء قدير. صلى الله على سيدنا محمد وعلى آله وصحبه وبارك وسلم. سبحان ربك رب العزة عما يصفون وسلام على المرسلين والحمد لله رب العالمين.
Alhamdulillah Rabbil Alamin. Okay, thank you very much. See you on Thursday. Now prepare
Okay, madam.
for your quiz. Okay, salam.
Madam,
Yeah?
yang quiz tu PN Junction je.
Yes, it will be only on PN Junction. Forward, reverse. Forward, reverse, zero. And everything that yang awak belajar sebelum tu, if it's related, you need to bring it up there. That is scattering ke apa-apa ke. Okay?
Is it in the class or like the quiz one?
Oh, this one will be closed book. I don't know yet. I haven't decide whether nak bagi dalam kelas ke, saya bagi lepas tu buat sendiri ke, tak tahu. Saya haven't decided. But this one will be closed book lah. Dan hari tu kan open book. So, but I trust you to not cheat. Okay, and Allah is my witness. Okay, any more questions? Tak ada? Let's end dengan tasbih kifarah and surah. Subhanakallahumma bihamdika asyhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. Bismillahirrahmanirrahim. Wal 'asr. Innal insana lafi khusr illa alladhina amanu wa 'amilus solihat wa tawassaw bil haqq wa tawassaw bis sabr. Awak semua buka puasa apa semalam?
Kurma.
Awak masak apa, ha? Apa?
Makan kurma.
Kurma ayam.
Korma.
Buah kurma, madam.
Buah kurma, ingat ke kurma tu? Tak, saya nak tahu lauk sebab saya nak fikir saya nak beli lauk apa. Cubalah. Awak makan apa? Share lah mak masak apa. Ha?
Saya pun lupa makan apa. Sekejap. saya fikir balik.
Astaghfirullah.
Apa ya? Salehin makan apa?
Gulai ikan masak dengan lanjut.
Apa?
Gulai ikan masak dengan lanjut.
Apa maksud? Tak pernah dengar benda tu apa? Gulai. Kenapa masak dengan lanjut?
Kan gulai kan, saya kan Negeri Sembilan. So macam kalau masak lemak cili api selalu masak dengan gulai, dengan buah lanjut ke.
Oh, buah tu, lanjut tu buah ke?
Lanjut tu buah.
Oh, saya tak pernah dengar buah lanjut. Dia rasa macam mana? Masam? Buah belimbing kot? Belimbing buluh
Tak, buah lanjut. Dia lanjut ni susah nak dapat. Macam sebab pokok tu selalunya berbuah dalam 5 tahun sekali.
Wow, specialnya makan. Bila nak bagi saya makanan sedap ni Salihin? Awak dah beritahu. Beritahu mak awak saya nak buah lanjut satu. Bukan nak buah, saya nak yang lauk siap. Kalau bagi buah tu tak jadi apa bagi saya. Dia akan buru situ. Aiman makan apa, Aiman?
Saya masak mi goreng.
Oh, sedapnya mi goreng. Mi goreng basah ke mi goreng? Okay, sorry akan mengganggu keimanan sikit. Mi goreng apa?
Dia basah dah bang.
Mak saya masak mi goreng sedap. Lama dah tak rasa mak saya masak. Okay, Hambali makan apa?
Simple je. Roti canai je.
Roti canai? Mau buat roti canai?
Ya. Makan ini macam tu lah. Masak nasi tomato lah.
Wah, sedapnya nasi tomato. Untung awak semua ni. Azam, makan apa?
Gulai nanas, lepas tu ada ayam masak merah.
Oh, sedapnya. Gulai nanas dengan ayam masak merah. Najwa makan apa? Boleh bercakap ke Najwa?
Madam, we are recording.
Allahu Akbar. Oh no.
Sorry.
We should not